In this video, we're going to look at projectile launches that are surface to surface. So last time we looked at horizontal projectiles in which we had a launch angle of 0 degrees. Now we have some non-zero launch angle. We're going to look at a positive launch angle. You can see my Nerf gun launcher over there on the left. It's inclined to some angle we'll call theta. Launches a projectile up. It travels in a parabolic arc or parabolic trajectory, which can be described by a quadratic equation, and eventually lands over there at the same height it was launched from, just further down the line, further down the floor of the road. Some important notes before we start. This is a type of 2D motion again, so we're going to have to analyze our x and y motions separately. We have a non-zero launch angle, so just be aware that now we have v naughts, or initial velocities, in the x and y direction that are not going to be equal to 0. Depending on whether we launch it with a positive or negative angle will determine whether those velocities are positive or negative. That, remember, depends on which directions we choose are also positive and negative. This example at left, very important, depicts a surface-to-surface launch. In this case, delta y, or the overall change in the vertical position of the particle, is going to be 0, because it's landing at the same height it was launched from. Alternatively there, I've drawn a couple brief sketches of what something else might look like, where you launch maybe from lower, and then at some angle it is able to go up and land at a higher target, or the opposite, you launch from a higher area and it lands at a lower target. In those cases, delta y would not be equal to 0, and the equations we're about to derive would have to be modified in order to fit that new scenario. Here's our t-chart again. I'm going to write out some of the stuff that we already know. Just like our projectile motion from before, we know that the vertical or y motion stuff is just free fall, and x motion stuff is with a 0 acceleration, so our velocities in the x direction are always going to be the same. Unlike last time with the horizontal projectile, we have an initial y velocity. Last time with the horizontal projectile, it was a condition of that horizontal launch that we had 0 initial y velocity. This is not the case now. So check out our green resultant, or total initial velocity vector there at the beginning. It is inclined at some purple angle theta, and it has component parts, or component vectors, that are the initial velocity in the y direction, v naught y in blue, and initial velocity in the x direction, v naught x. We can say more specifically what these are in terms of the angle theta because we know how to use our trig relationships. I can also write those values in for my t-chart to help me just keep track of stuff. I'm going to mark up some times in pink there, t naught through t final. I'm also going to put in, just for a reminder, our red velocity vectors vx are equal to v naught x, which is equal to v naught cosine theta. This value does not change throughout the entire motion because it is the assumption that this also, in projectile motion, has the same conditions as free fall. The only force acting on the object is gravity after it leaves the projectile launcher. There's no air resistance to slow it down or accelerate it in the opposite direction. So those Vx velocities in the x are constant, same value. In blue I have my velocities in the y direction, somewhat proportionately drawn. As the thing is launched, it travels through the air to the top of its trajectory, all the while losing some velocity in the positive y direction until it comes to a stop momentarily with a 0 y velocity at time t3. After t3, it gains velocity in the y direction, but in the negative y direction, and that increases until its final impact down at t sub f, or t final. I also, remember, have a constant acceleration in the y direction that is equal to g. In this case, since I've called down negative, it's minus 9.80 meters per second squared. And that is an acceleration that is constant at every single point of the trajectory. The object has a y acceleration that is equal to g, even at the top where it comes to a momentary stop. I'm going to draw in my resultant velocity vectors for each of those other places, t1, 2, t3, t4, t5, and t final. And notice at t3 there is no green arrow for me to draw because the only velocity vector there is the horizontal x component. That is the total velocity at that time t3. The other ones I have my green arrows drawn showing my resultant, which is just the geometric addition of those two red and blue vectors. I can write my y final velocity there as being the same as my initial y velocity, but in the opposite direction. Just like in free fall, if I toss something straight up, it comes straight back down without air resistance. It'll have the same final velocity that it'll hit my hand as it did when it left my hand. It hits my hand with the same speed as I threw it up. And it's going to be the same for the case of the projectile motion because that y motion is just like free fall. Our delta y is 0. That was part of the condition of this example where we do a surface-to-surface launch where there's no overall change in height. So just as a reminder again, if it is a different example where you're hitting a different target higher or lower than your original launch height, then some of this is going to change. The overall idea and concepts, though, are no different. Delta x down on the left on my t-chart I've drawn out as v0 cosine theta times t, since we have another way of writing v0 x. We write it as v0 cosine theta. This is great when we have the actual value of v0, perhaps it's given in the problem, and we know our angle theta. That value there is just the velocity in the x direction, and then times time gives us the range, or the horizontal displacement of the particle delta x. Much of what we're doing in analyzing this is just the same as the horizontal projectile and other two-dimensional motions. We do need to remember to keep track of our different types of motion in the x and y direction, and that's why the t-chart is there, because it's so helpful to do so. We're still going to be careful to organize those and relate them to our kinematic equations to solve whatever unknown quantities that we need. There are a few things that I want us to be able to find when we look at surface-to-surface projectile launches, or any projectile launch at an angle, and that one of those things is total air time, sometimes written as t sub air. I want to write it as t sub t. So that's the total amount of time tf minus t naught things in the air. We also want to be able to say what the maximum height is that the projectile reaches, and that's going to be the point at t sub 3, or time 3. That's where it reaches a maximum height, sometimes written as capital H. The third thing I think we need to be able to talk about is what launch angle produces the greatest range. So that talks about the range. Again, we just mentioned what the range is, that total displacement in the x direction, all the way from the beginning to the end of its trajectory. I'm going to skip ahead to get our drawing fully out there. There it is. And we'll start with number 1, looking at the time. The total time is going to be the change in position is 0 of this parabola. Notice that the object's going to be launched and it's going to reach its highest point and come back down to its original launch height. So its total vertical displacement is 0. I've chosen to use that kinematic equation delta y, or change in position, equals initial velocity in the y direction times time minus 1/2 g, the acceleration due to gravity, times time squared. Delta y is 0. I substitute that value in. V0 y is an unknown value. I'm going to leave it as it is right now. Times t in pink is going to stay t. That's the value you want to solve for. Minus 1/2 g. That's minus direction, gravitational acceleration. Down is negative, so I have my minus sign there. And then I have t squared again over there. Again, the pink t, the value I want to solve for. We can recognize this as a quadratic equation, and we're going to use a quadratic formula to solve it. Notice I've written out my quadratic formula, and I've written which parts of my equation correspond to the A, B, and C components of that quadratic formula. There I go substituting in those values. Notice that that portion of the numerator that I've just bracketed in blue, that's under the radical, is going to become 0 because my component C of the quadratic formula, that final constant with no coefficient, that final coefficient with no t variable, rather, is 0, so that portion under the radical goes to 0. That's going to leave me with v0 y plus or minus the square root of v0 y squared over g. Those minus signs before in my numerator and denominator are going to cancel out. This should look familiar from one of the questions we had on the quiz. Now, look at that square root of v0 y squared. That's just going to be v0 y. So my two options here, plus or minus, are going to be v0 y plus v0 y, which will give me 2 v0 y, or twice the initial velocity in the y direction over g. Or if I subtract, I'll get 0 over g. This gives us a couple things to think about physically as well as mathematically. This quadratic equation, or quadratic formula for solving the quadratic equation, finds me essentially where the function crosses the x-axis. In this case, the parabola is crossing at 2 different points. One when time equals 0, and again when the time is the final time, back when it lands at its final destination at t sub f. So one of my solutions is when time equals 0, hence I have 0 over g. My other solution is 2 v0 y over g. That's going to be the amount of time in seconds that I have to get to t sub f, the final point where the function crosses over the x-axis again. So there's our difference. One is t naught and one is t sub f, and this can also be written as t v naught sine theta, since we show that that's what the y component of the initial velocity is equal to if we have the original velocity and the angle theta. So we put a box around that. That's how we can find our total time, or t air. The next thing we want to look at is number 2. What is the maximum height that it can reach? That's a physical looking picture of where the max height is. It'll be some vertical delta y displacement from time 3 minus time naught. So it's right there halfway through the trajectory. And I have one thing I know about this position is that the velocity v3 is going to be equal to 0. Think again, just like the free fall, if I throw something straight up, there's a point at which it stops and is momentarily with a velocity of 0, and that's when it's at its highest point. So I know if I use the kinematic equation v naught, or final velocity in the y direction, equals v naught y, the initial velocity in the y direction, minus gt, I can substitute in 0 for final y velocity if I'm talking about the period of time between t naught and t3. The object comes momentarily to a rest vertically at time t3, and if I solve for time there, I have t equals v naught y, the initial velocity in the y direction, over g. And again, that v naught y can be written as v naught sine theta when we have that original velocity v naught and the angle theta. Notice real quick that this amount of time here is simply half of the total time. The total time we just solved for in box 1 was 2 times v naught sine theta over g. And we just found the time to get the highest point, which is halfway through its trajectory, and that's v naught sine theta over g, half of what we just found. So this makes good sense. It is also only correct when we have a surface-to-surface launch. Think about why that is for a minute. What am I writing next? Delta y equals v naught yt minus 1/2 gt squared. We are now using this time to find out what the total vertical displacement is, and I'm writing that out now as capital H. So that's that. Look back at the diagram. The height it travels from t naught to t3, halfway through its trajectory at its highest point, and so I'm substituting directly in to that equation kinematic equation I have v naught y t minus 1/2 gt squared. v naught y is v naught sine theta, and I've written that as a fraction v naught sine theta over 1 to keep track of my upstairs and downstairs portions of my fractions. I have a time t, which I just solved for, the amount of time it takes to get from t naught to t3, halfway through the trajectory and at its highest point. And that amount of time is v naught sine theta over g. That's some value that then I'm going to say minus 1/2 gt squared, so I have 1/2 times g over 1, again just to keep track of my upstairs and downstairs portions of my fractions, times t squared, and if I square the time I just found, I get v naught squared sine squared theta over g squared. Sine squared theta is the exact same thing as saying sine of theta and that squared. We just often write it as sine squared theta. So when I solve this now, I have a g upstairs and downstairs that cancels out. And then I have v naught squared sine squared theta over g minus 1/2 v naught squared sine squared theta over g. So what does that leave me with? It leaves me with 1/2 v naught squared sine squared theta over g. Or as we'll be used to seeing it and writing it, v naught squared sine squared theta over 2g. That's my maximum height. We can think about that physically. So a lot of the type of questions that are quantitative reasoning questions on the AP exam will say something like, if I double the gravitational acceleration, what will happen to the maximum height of this projectile? Well, being able to derive this equation and show that if I double the gravitational acceleration, that's going to be inversely proportional to the maximum height. So that's how it's going to affect the height. I can see that g is on the downstairs of my equation, and it makes sense if I increase the gravitational acceleration, how quickly the thing is accelerating towards the ground. It's not going to be able to achieve as high a height as if I have a lower gravitational acceleration. Similarly, another kind of quantitative reasoning question might be, if I double the initial velocity, v naught, if I double v naught, what's going to happen to the height? Max height that the projectile can achieve. And you can see from the equation that the height is directly proportional to v naught squared. So if I double v naught, if I double the initial velocity, my height will actually be squared of that. So it'll be 4 times higher. That's an important thing to be able to reason through quantitatively, not necessarily just numerically. We're going to put a box around that. They're just a reminder for my max height equation that v naught squared sine squared theta is the same thing as the initial velocity in the y direction squared. And that's all that v naught sine theta is just the initial velocity in the y direction. The last thing we'll look at is the maximum range. The range equation that we used before for horizontal projectiles was just basically distance equals rate times time. The velocity in the x direction is the same. We multiply it by the time, or rather the velocity in the x direction stays the same throughout the entire projectile's trajectory. Multiply that by the time and you get the delta x, or horizontal displacement, or the range. Here we're going to write out what that is, given that we say no v naught in green. So if we want to use vx, or the velocity in the x direction, just the x component of that initial velocity, then we say v naught cosine theta. And that multiplied by the time, the total time that we solved for, which was twice v naught sine theta over g, twice the amount of time it takes to get to the highest point. Then when we combine those, we get v naught squared minus twice sine theta cosine theta. 2 times sine theta cosine theta over g. Now there is a trig identity that is relevant to this portion I just bracketed in light blue, and that's sine of an angle plus another angle equals, oh, that's very disjointed, that's kind of weird looking. The sine of an angle plus another angle equals the cosine of that angle times the sine of that other angle, in this case alpha and beta, plus the sine of the first angle times the cosine of the second angle. When we add these together, if they're the same angle, for instance, if I'm saying sine of twice that angle, and there's the bottom part is the important thing to look at, this part down here, that's the trig identity that we care about. The sine of twice the angle is equal to 2 times sine of that angle times the cosine of that angle. So that's what we have in our numerator right now, is 2 times the sine of the angle times the cosine of that very same angle theta. That's the same as the sine of 2 times that angle theta. So we're going to substitute that back into the very top up there, and we're going to get the range equal to v naught squared times the sine of twice theta over g, and this is going to be our range equation. If we ask what's the maximum range, or what do we have to do, what angle do we have to launch a projectile at in order to achieve maximum range, we need the sine of twice that angle, that entire expression right there, to be equal to 1. So I ask myself, what must theta be for that expression to be equal to 1? The sine of some value can range between 0 and 1, so 1's the maximum it can be. That's what we need to try and make it if we're going to make this entire expression v naught squared sine 2 theta over g be as large as an expression or value as possible. So how do I get that expression to be equal to 1? I need to think what angle needs to make it 1, and that's going to be 45 degrees, as we showed right there. So 45 degrees provides the maximum launch range, and that's something that we can see from the mathematics. We also have values that are complementary, such as a 30-degree launch angle and a 60-degree launch angle. And so here I've brought up our 4 equations that we just talked about. Over there on the left is total air time, which is twice the initial velocity times the sine of the angle theta. That's the launch angle over g. Our time to get to the top or highest point is the initial velocity times the sine of the angle over g, or just half of that first equation. Our maximum height is found by squaring the initial velocity and sine squared of that launch angle, or sine of the angle, evaluate that, and then square it, divided by 2g. And then our range equation for a surface-to-surface projectile launch is v naught squared times the sine of twice the launch angle theta over g. And these are kind of the special projectile equations that can be derived, and they are not really worth memorizing, but being able to derive them is very good practice, and thinking about what they imply, like determining what's the maximum range you can get out of launching a projectile, find how can you justify what angle should give you the maximum range. That's a really good exercise in that type of quantitative reasoning we want to be able to do. Same like before when I talked about the height equation there. What happens to the height if I double the initial velocity? It's good to be able to say quantitatively what's going to happen without going through an entire equation and plugging in actual numbers. The College Board cares much more about whether you can reason through it quantitatively after deriving the equation. There are a few other images I've thrown up here from Knight's college physics book and Eugenia Ekina's college physics book. These are just some images to help us work through some of the ideas of projectiles from surface to surface. And notice that complementary angles will have the same range. That's something that also falls out from that equation that you can test using the range equation. And there's also a picture at the top right that shows velocity vectors and a reminder that acceleration is always pointing down to the ground and has the value minus 9.80 meters per second. That's meters per second squared if we are calling down negative. We will have some more videos on actual problems to practice with. Some will be quantitative solutions to projectile problems. Others will just be kind of the quantitative reasoning or more AP style questions.